I did the derivative at the value of a at one point. But I want you to think of it more in terms of a function. I could do this same computation at any a. I did it at this one here, but I could do it for a b or a c or anything. So I'm going to actually replace it by thinking of this derivative as a new function. I write f prime of x, where x usually denotes a variable in a function, and a is like a specific specified point. But I do the exact same thing. F of x plus h minus f of x all divided by h is the derivative at the value of x when I take the limit as h goes to 0. I'm thinking of this as a function. That is, if you give me some function f, I could go and do this computation and hopefully come out with another function, the derivative of the function you gave me. So let's see an example of how that might work. I want to compute the derivative of 1 over x. And geometrically we can think, well, 1 over x is some curve, and it should tell me what the slope is to that particular curve. But I'm going to do this purely algebraically. So how does it work? What did we begin with? A limit as h goes to 0. And then I have to write, first of all, f of x plus h. So I've got 1 over x. I'm going to come in here and write 1 over, everywhere there's an x, I put in x plus h, so x plus h. So that's my function evaluated at x plus h. Now I want to subtract off my function evaluated at x. That's easy enough to do. Subtract off just 1 over x. So this is f of x plus h. Subtract off f of x, and then I'm dividing the entire thing by h. Now, this looks like a bit of a messy thing, but anytime where you have a difference of fractions, the standard canonical algebraic trick is to find a lowest common denominator. So let's do that. So I'm going to copy and paste the limit part. I'm going to copy and paste the big denominator down here, or the divided by h. That's not going to change at this step. But now I'm going to do lowest common denominator to this portion up here. So I'm going to say that what I have is an x minus x plus h, and then this is all divided out by x multiplied by x plus h. So I've done that little algebraic trickery. Now, I want you to notice that up here at the top, I've got an x, and then I subtract off an x. So let's get rid of those. I don't need those any longer. And so what I have on this top, this whole sort of top portion here, this is just the same thing as the value minus h up there on the top. But then I have an h on the top, and I have an h down here on the bottom, and so that h and that h are going to cancel as well. And so what this leaves me with, if I'm being careful with my signs, I'm going to copy and paste the limit as h goes to 0. That never changes. But I still have the minus sign here in front of the h. The minus, I'll make it a minus 1 now that the h cancels. So minus 1 divided by x plus h. Okay, it got a little simpler, that's good. But what else can we do? Well, now this is the limit that I think I can evaluate what happens as h goes to 0. I can use my different limit laws. This is a rational function. So I'm just going to set h going to 0 right now. And what is this? It's minus 1 divided out by x squared. Notice this final step here is the only time I do not put a limit. I always do limit of my expression equals limit of my expression equals limit of my expression. And then this step here, I'm evaluating the limit. I'm distributing it through. I'm setting my h to 0. And so I get rid of the limit sign at this final step here and write minus 1 over x squared. And so I claim that this is equal to f prime of the function x. Now I want to be clear. You might say, well, hold on, Trevor. If at this final step, you just made h equal to 0, why didn't you just make h equal to 0 at the beginning, at the first step? Well, I'm not allowed to do that because this division by h on the bottom here means that I'd have a division by 0. I can't just naively plug it in. I have to go and do this algebra until I have a scenario where when plugging the h in, when making that equal to 0, this does not result in any discontinuity, does not result in any divisions by 0. So that's why when I've done my algebra to get it down to this step, now I can plug in the h equal to 0. It's a continuous function at that point, and I get it equal to this. By the way, the original function f was not defined at 0. its derivative not defined at 0 as well. So this entire analysis I've done, everything is only relevant in the scenario where x here is not equal to 0. I don't even have a conversation when x is equal to 0. The original function isn't even defined. Does it make sense to say what is its derivative going to be? So this kind of algebraic procedure, by the definition of the derivative, is how I can start with functions and come up with their derivatives. Or geometrically, if I have some function like 1 over x, it can tell me what is the slope of that function at any particular value of x, and that is going to be the answer.